Physics has no objection to this video playing in reverse right now. A billiard ball rolling backward, a shattered glass reassembling itself, air flowing back into your lungs. All of it is perfectly consistent with the laws of physics. The equations work in both directions. No law forbids time from running backward. But time doesn't run backward. And that is one of the most disturbing questions science has never quite taken seriously enough. Let's start with something simple. You drop a coffee cup. It falls, hits the floor, shatters into pieces. Now imagine that scene playing in reverse. The fragments leap off the floor, fly upward, reassemble perfectly in midair, and land intact in your hand. You watch that and immediately know something is wrong. It looks absurd. It looks impossible. But here is the thing. If you write down the physics of every fragment of that cup, every particle of air it disturbs, every vibration it sends through the floor, and you reverse all the velocities, every single equation remains valid. Newton's laws, satisfied. Conservation of energy, satisfied. Conservation of momentum, satisfied. The reversed scene is not forbidden by any law of physics that governs the particles involved. The universe, at the level of fundamental equations, cannot tell the difference between forward and backward time. This is not a philosophical trick. This is one of the most verified facts in all of physics. Take any interaction between particles, any collision, any force, any quantum mechanical process, and reverse the direction of time in the equations. What you get out is another valid physical process. The equations are time-symmetric. They treat the past and the future identically. There is no arrow built into the fundamental laws, and yet you have never once seen a shattered cup reassemble itself. You have never watched smoke pour back into a chimney, unburning the wood as it goes. You have never seen a ripple on a pond converge from the edges toward the center, rather than spreading outward. The world has a direction, but the laws don't. That gap, between the symmetry of the laws and the asymmetry of everything you have ever experienced, is what physicists call the arrow of time. And it is, depending on who you ask, either almost understood or completely mysterious. Here is the deeper problem. It is not just one arrow. There are several, and they all point the same way, and nobody fully understands why they are synchronized. There is the thermodynamic arrow, the direction in which disorder increases. There is the cosmological arrow, the direction in which the universe expands. There is the radiative arrow, electromagnetic waves spread outward from a source rather than converging inward toward one. And there is the psychological arrow. You remember the past and not the future. All of these arrows agree. They all point in the same direction. But the fundamental physics they are built from doesn't have a direction at all. So where does the arrow come from? Why does every single process in nature conspire to point the same way, when the laws governing each individual process don't care which way they point? The standard answer involves a 19th century Austrian physicist named Ludwig Boltzmann, and a concept you almost certainly learned in school but probably never thought about long enough to find genuinely disturbing. The second law of thermodynamics. The law that says entropy, the measure of disorder in a system, never decreases in a closed system. It stays the same, or it goes up. Always. Ice melts in warm water. It doesn't spontaneously freeze. Perfume spreads through a room. It doesn't gather back into the bottle. Heat flows from hot objects to cold ones, not the other direction. And it is this law, most physicists will tell you, that gives time its direction. The cup shatters and doesn't reassemble because the shattered state has vastly more disorder than the intact cup, and the universe prefers disorder. Things fall apart. They don't spontaneously come back together. Entropy increases. Time moves forward. Arrow explained. Except that explanation has a flaw so deep it nearly broke Boltzmann himself. Here is the flaw. The second law is not actually a fundamental law. It is a statistical one. Boltzmann himself showed this, and it was one of the most important insights in the history of physics. The reason entropy tends to increase is not that physics forbids decreases. It is simply that disordered states are astronomically more numerous than ordered ones. Think about a box with 1,000 gas molecules all clustered in one corner. There is exactly one way to have all 1,000 molecules in that corner. There are an almost incomprehensibly large number of ways to have them spread throughout the box. So spreading out is what happens, overwhelmingly, almost all the time. Not because a law forces it, but because the odds are staggering. The second law is probability dressed up as law. And this was brilliant. But here is where the trouble begins. Probability cuts both ways. If you take a system in a high entropy state and run it forward in time, entropy will almost certainly increase, or stay the same. But if you take that same system and run it backward in time, entropy will also almost certainly increase in the backward direction. The statistical argument is symmetric. It doesn't prefer either direction. If you came across a room where all the air molecules were clustered in one corner, the statistically overwhelmingly likely explanation would not be that they started spread out and happened to cluster, because that is fantastically improbable. The far more likely explanation is that they were in an even more clustered state a moment ago and are now dispersing. Entropy increasing toward the future is statistically likely, but entropy having been lower in the past is also statistically likely. The argument, applied consistently, gives you a low entropy past and a low entropy future in equal measure. It cannot, by itself, explain why we only experience the arrow in one direction. Boltzmann saw this. It haunted him. He spent years trying to find a satisfying resolution and, by most accounts, never did. The critics of his time argued that the time-symmetric nature of his statistical mechanics proved it couldn't be the right foundation for an asymmetric arrow of time. They were, in a deep sense, correct. He died in 1906, by his own hand, most historians believe, without resolving the problem. The core question he couldn't answer is still, in its deepest form, unsolved today. Wait. What this actually implies is stranger than it might first seem. If the laws of physics are symmetric, and entropy increases in both directions from any given moment, then the real question is not why entropy increases toward the future. That part is just statistics. The real question, the question that actually explains the arrow, is why entropy was so extraordinarily low in the past. Why did we start in such an ordered state? The reason the cup shatters and doesn't reassemble is not that physics prevents reassembly. It is that the cup, before you dropped it, was already in a condition of extremely low entropy, intact, ordered, whole. And the reason the direction goes from order to disorder rather than from disorder to order is not a law. It is a fact about where we started. The arrow of time on this account is not a feature of the laws at all. It is a feature of the initial conditions of the universe. And that pushes the question all the way back to the Big Bang. The universe, at the moment of the Big Bang, was in a state of almost unimaginably low entropy. Not low temperature. In fact, it was extraordinarily hot, hotter than anything that has existed since. But thermodynamic entropy is not just about temperature. It is about the number of ways a system can be arranged while still looking the same from the outside. And the very early universe, despite its heat, was extraordinarily smooth, extraordinarily uniform, extraordinarily ordered in a gravitational sense. Gravity is the key here, and it makes the story strange. For most systems, a smooth, uniform distribution is a high entropy state. Molecules spread evenly through a box have more entropy than molecules clustered in one corner. But gravity inverts this. Under gravity, clumping is the high entropy state. A smooth universe full of matter is, gravitationally, a very low entropy state, because gravity has enormous room to pull things together further, to form stars, galaxies, clusters of galaxies, and ultimately, black holes. The early universe was smooth. It was gravitationally ordered. It had an enormous reservoir of available entropy yet to be released. Everything since, stars forming, burning, exploding, galaxies assembling, black holes growing, planets condensing, life evolving, you sitting here reading. All of it is that entropy reservoir being gradually spent. The journey from the smooth, early universe to the cold, dark, evenly distributed late universe is a journey from low entropy to high entropy. That journey has a direction. That direction is what we call the future. And the reason your cup doesn't reassemble, the reason smoke doesn't flow back into chimneys, the reason you can't unspeak words or unfeel moments, is that all of these processes are steps along the same thermodynamic journey that began 13.8 billion years ago in an extraordinarily smooth, extraordinarily ordered, extraordinarily improbable initial state. This is sometimes called the past hypothesis, the assumption that the universe began in an extremely low entropy configuration. Most physicists accept it as a working assumption because it is the only framework that correctly produces the unidirectional arrow we observe. But it raises an immediate and deeply uncomfortable question. Why did the universe start that way? A low entropy initial state is, statistically, an almost impossibly special initial condition. If you were to choose the initial state of a universe at random, the overwhelming majority of possibilities would be high entropy, already disordered, already uniform, with no arrow available to release. The fact that our universe started in such a specific, ordered, low entropy state is one of the most profound and unanswered questions in all of cosmology. Some invoke inflation, the rapid expansion of the very early universe, as an explanation. Some invoke quantum cosmology and the idea that the universe tunneled into existence through a quantum process that preferentially selects low entropy beginnings. Some simply treat it as a brute fact about which universe we happen to find ourselves in. None of these explanations is fully satisfying. The honest position is that we don't know. Here is where it gets stranger still, and this is the part that tends to rearrange things permanently. In 1867, the Scottish physicist James Clerk Maxwell, the same Maxwell who unified electricity and magnetism, described a thought experiment that seemed to defeat the second law entirely. Imagine a box of gas divided in half by a wall. In the wall is a tiny door, controlled by a tiny imaginary demon. The demon watches molecules approaching the door. When a fast molecule comes from the right side, he opens the door and lets it through to the left. When a slow molecule comes from the left side, he opens the door and lets it through to the right. Slowly, over time, the left side fills with fast molecules, and the right side fills with slow ones, hot and cold, ordered and separated, without any apparent work being done. Entropy has decreased. The second law appears to be violated. For 70 years, Maxwell's demon haunted thermodynamics. Then, in 1961, physicist Rolf Landauer showed what the demon's fatal flaw was: memory. To sort the molecules, the demon has to measure each one and remember the result. And erasing that memory, resetting the demon's information to start fresh, necessarily generates heat. That heat increases entropy by at least as much as the sorting decreased it. The second law survives. But what Landauer's insight revealed is something profound. Information is physical. Erasing a bit of information has a thermodynamic cost. Memory and entropy are not separate concepts. They are the same concept seen from different angles. And that connection between information, memory, and the arrow of time runs all the way through to why you experience the present as the present and not some other moment. Think about what the arrow of time means for memory. You remember the past. You do not remember the future. That feels obvious. But push on it. What is memory, physically? Memory is a record, a physical arrangement of matter that encodes information about a previous state of the world. A photograph retains light patterns from a moment that has passed. A footprint in sand encodes the pressure of a foot that is lifted. A neural connection in your brain encodes an experience that has ended. All of these are physical structures created by entropy-increasing processes, marks left on a world moving from order toward disorder. And crucially, records can only point toward the past because the process of making a record itself increases entropy. You can't leave a footprint in sand in the future direction without the sand, the foot, and the entire surrounding environment already being in a specific arrangement. Records require low entropy starting conditions in their causal past. So the reason you remember the past and not the future is the same reason cups shatter and don't reassemble: the low entropy beginning of the universe. Your memories point backward in time because the physical processes that created them required a source of low entropy to draw from, and the only available source of low entropy runs in the direction we call the past. Your psychological arrow, the subjective sense that time moves, that the now is special, that the past is fixed and the future is open, is not a fundamental feature of reality. It is a consequence of your position in a thermodynamic story that started with an improbably ordered universe. That is not a metaphor. That is the best physical account we have for why you experience time the way you do. But wait, there is another layer, and it comes from the deepest physics we have. Quantum mechanics adds a twist that is still not fully resolved. Almost all quantum mechanical processes are also time-symmetric. A particle decaying, a photon being absorbed, two electrons scattering. Reverse the time in the equations and you get another valid physical process. Almost. There is a small class of processes involving the weak nuclear force, the force responsible for certain kinds of radioactive decay, that are not perfectly time-symmetric. In 1964, physicists James Cronin and Val Fitch discovered at Brookhaven National Laboratory that certain decays of particles called kaons behaved slightly differently depending on which direction time ran. This was one of the most unexpected results in 20th century physics, and it earned them the Nobel Prize in 1980. This asymmetry is called CP violation, and by a deep theorem of quantum field theory called the CPT theorem, CP violation necessarily implies T violation, actual time reversal asymmetry at the level of fundamental particle physics. The laws, at the level of the weak force, are not perfectly symmetric under time reversal. They have a slight preference. But here is the puzzle. The effect is tiny. It doesn't obviously explain the large-scale thermodynamic arrow we experience every moment of our lives. The connection between CP violation at the particle physics level and the macroscopic arrow of time remains one of the genuinely open problems in fundamental physics. It may be that the two are deeply connected and we don't yet see how. It may be that they are largely independent. CP violation a subdominant effect, the main arrow coming from the past hypothesis. Nobody knows for certain. There is one more idea worth sitting with, because it changes not just how you think about time, but how you think about existence itself. Some physicists, drawing on the mathematics of general relativity and the block universe interpretation that falls out of it, have proposed that time does not actually flow at all. That the experience of time moving forward is a feature of how a certain kind of conscious system processes information, not a feature of reality at the physical level. In general relativity, time is just another dimension. The equations describe a four-dimensional spacetime in which all events, past, present, future, exist with equal ontological status. There is no preferred now. There is no flowing present moment. There is just the space-time manifold and the events arranged in it, related by causal structure, with no built-in direction of flow. On this view, what feels like the passage of time is what it feels like to be a physical system that contains memories running in one thermodynamic direction. You exist at one moment. A slightly different version of you, with a slightly longer memory, exists at the next. Both are equally real, equally present in the block universe. Neither is more now than the other. The sensation of flow is the subjective experience of a system whose internal information structure is asymmetric in one temporal direction. You feel time moving because your brain contains records of the past and not the future, because entropy runs in one direction, because the universe started in a low entropy state. Remove those initial conditions, and the subjective flow of time would not exist. Or rather, it would run equally in both directions, and the concept would dissolve entirely. That is not a consensus position. It remains contested in both physics and philosophy, but it is taken seriously by serious people, and it illustrates how far the question of time's arrow reaches. It reaches all the way into the question of what it means to experience anything at all, into the nature of consciousness, into the question of what the present moment actually is. These are not separate philosophical questions. They are downstream consequences of the physics of entropy, which is downstream of the initial conditions of the Big Bang, which is downstream of something we cannot yet explain. Here is the thing that lands hardest when you really sit with it. You go through your entire life with an overwhelming, unquestioned sense that time moves in one direction. The past is fixed. The future is open. The present is real and fleeting and unrepeatable. This is so fundamental to how you experience existence that questioning it feels like questioning existence itself. And then you learn that the laws governing every particle in your body, every electron, every quark, every photon crossing the room, are completely indifferent to which direction time runs. That if you reversed all the velocities of all the particles in the universe simultaneously, physics would have no objection. That the arrow you experience with such overwhelming certainty is not written into any law. It is written into the initial conditions of a Big Bang 13.8 billion years ago. And that those initial conditions, the thing that gives you your memories, your sense of self, your irreplaceable experience of this present moment, are themselves unexplained. Physics can trace the arrow back to the beginning. It cannot yet tell you why the beginning was that way. The universe, at its most fundamental level, does not know which way time goes. You do. But only because of where everything started. And nobody knows why it started there. If you have ever stood somewhere and felt time, really felt it, the weight of a moment you knew was passing, the impossibility of return, leave a comment. Which part of this landed hardest? The symmetry of the equations? The fact that the arrow traces all the way back to the Big Bang? The idea that your memory, your sense of self, your experience of now, are all thermodynamic phenomena? Or the possibility that time doesn't flow at all, that you are simply a system that remembers in one direction? And if you want to keep following questions like this, questions that start familiar and end somewhere you didn't expect, subscribe, because that is exactly what this channel is for.